Hello and welcome to section 1.3, the topic of vector space Rn. In this video, we want to really kind of generalize what we know about linear systems and see if we can develop a more general way to talk about these things. Let's recall that when we considered possible solutions of linear systems, we saw that the solutions, if they exist, consist of either a point or maybe a plane or line full of points, right? So the solution sets to these systems consisted, when they existed, they consist of either a point or some set of points, like a line or a plane, right? But these solution spaces, that line or that plane, these are just subsets of the larger space that they sit in, right? If I have a line in 2 dimensions, that larger space that subset is, that subsets in, is this 2-dimensional plane. A plane, for example, as a subset, would be a subset of 3-dimensional space, of the 3D space. So we want to, in order to really develop general information about the solutions of linear systems, we're going to need to talk about the idea of vector spaces. And we're going to start out with kind of the most tame and intuitive vector space Rn, as we'll see. So let's get into this. A point in 2D is located with 2 coordinates. Right? That makes pretty easy sense. No matter what coordinate system you use, whether it's rectangular XY coordinates or maybe polar coordinates, doesn't matter. In the plane, to identify points, you need 2 coordinates, regardless of that coordinate system. For example, you could plot the point 2, 1, labeled that as point A here. And I've plotted that in the plane. That's that dot here out at 2, -1. Well, so if we're considering any point like this point A out in the plane, it's always got some distance to the origin. So we can define what we call the position vector, OA, with this little vector harpoon over it, this little arrow over it to indicate this is a vector quantity. We can define the position vector OA to be a directed segment with direction and length describing how to get from the origin to A. Right, the direction will tell you, right, which direction to go from the origin, and the length of this OA position vector will tell you how far to go in that direction. So from the origin to get to A, the position vector OA tells you you need to go kind of downward and to the right, or a certain amount of length, just this distance from O to A. Right, so any point in the plane we can describe with this position vector for the point. When we do that, when we describe OA this way, that initial point O, in this case I've drawn it at the origin. We always call the starting point of one of these position vectors an initial point. Really, for any vector we call that the initial point. And A is the terminal point, right, where it stretches out to before ending. So any ordered pair like 2, -1, and this is really important here, can be interpreted as a location of a point in the plane. So right, it can be interpreted as a set of coordinates, or it can be interpreted as defining a position vector. Instead of thinking of 2, -1 as representing just this point here, we can think of it as representing the position vector stretching from the origin to this point. Right, and if you've gone through a Calculus 3 class, you've probably got some experience with this sort of understanding that you have points in space, but somehow those same coordinates can be thought of as defining a position vector of that point. Okay, so let's go a bit further here. We denote all sets of, we denote the set of all ordered pairs of real values by R2. And it's pronounced as I've written here, R2. And notice, in these sets of ordered pairs, we're going to say that the order that we write them in matters, because in our common understanding of these points like we have up here, right, 2, -1 is certainly different. It's not the same as -1, 2. So the order that we pair these numbers up in really does matter. That takes us to a whole different point in the plane, or gives us a whole different position vector, if we want to think of it that way. But so these pairs of numbers like this, pairs of real numbers, we consider them to be, thinking graphically like this, the set of all possible ordered pairs like that we consider to be R2. Okay, a specific set of mathematical set defined as R2. Now, if we wanted to extend that to 3D, we denote the set of all ordered triples of real values by R3. Right? Elements of R3 can be interpreted as points in the 3D Cartesian XYZ space, right? Or as a position vector. Just like in 2D, a point out here can represent a position in the plane, or it can, that same set of numbers, 2, -1, could represent the vector from the origin to that point. In the same way, we can think about 3D space. A point 2, 1, -2, for example, could be thought of indeed as a set of coordinates, a point. Or we can think of those same coordinates as representing all the information related to a position vector from the origin to that point, right? An arrow that stretches from the origin out to that point. So when we are talking about these ordered pairs or these ordered triples, we are always kind of going to keep in mind this dual meaning. They can represent positions in space or the plane, or they can represent position vectors. We will mostly be thinking of these as position vectors, but keeping this kind of spatial coordinate interpretation will also be important. Okay, so let's go a little bit further here. Well, we saw how we think of R2. We saw how we think of R3, the set of all ordered triples of real numbers. We want to generalize this same idea to Rn, the set of all sequences of real numbers where you have n of them all together. Instead of an ordered pair or an ordered triple, here you have n numbers all ordered in a specific way. So the set of all those possible things you could come up with of this form, where u1, u2, all the way out through un are all real numbers, is denoted Rn. Let's see here. Seems like I wanted to mention something else about that. I guess not. So just like with R2 and R3, we will refer to those numbers in this ordered N-tuple. You can think of it instead of as being a pair or a triplet. We often call this an ordered N-tuple, meaning it has n entries. In something like that, we'll refer to these actual numbers in these real numbers, u1, u2, and un. We will refer to u1 as the first component of that element of Rn, this u1, u2 all the way out through un. That is just a single element of Rn. The first number in that element we call the first component. The second number, u2, we call the second component of this element of Rn, and so on. So each of those numbers is a component of this vector, or you can just think of it as an element of the vector space Rn. So I wrote a couple examples down here. If we were asked to write down just any element of R5, just to show we understand what we're talking about here, well, here's a decent example of some element of R5. It's just an ordered list of 5 real numbers. That's all it is. R10, I've written some pretty arbitrary list of numbers here. That's certainly 10 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Any ordered list of 10 numbers is an element of R10. And so keep in mind, we can't easily visualize much about Rn if n's bigger than 3. Right? R2 we have an understanding of. Even R1, just the number line, that's pretty easy to understand. R2 is the plane. R3 is the standard three-dimensional space we often think of. But for n bigger than that, it's difficult to think visually about what we're talking about. But we just generalize. The way we think about these things in R2 and R3, we just generalize that and say, that's how we'll do things in Rn. And we find that's a very useful way to proceed. Right? The elements of Rn, no matter how big n is, can be considered points in n-dimensional space. If n's bigger than 3, we can't really imagine it. Trapped in our three-dimensional spatial thinking, n could certainly be bigger mathematically. So any elements of Rn can be thought of certainly as points in n-dimensional space, or just as position vectors in n space. Right? This is, you might hear the plane referred to as 2 space, or R3 you might hear referred to as 3 space. you might hear Rn referred to as defining this N space. Okay, so let's talk about how to deal with these elements of these spaces, Rn. Let's see here. Given I'll call this a vector in Rn, given a vector in Rn, vector u1, u2, u3, all the way out through un, being the last number, the last component of u, and a vector v in Rn given by components v1, v2, v3, again, all the way out to vn, and a scalar c, we can define addition of these elements of Rn, addition of these vectors, as u plus v, so this guy plus this guy. If we know its components, we're going to say the addition is just the component-wise addition of the two vectors. The first component of the sum is the sum of these first two components, u1 and v1. The second component of the sum is the sum of the second two components, u2 and v2, and so on, all the way up to the end. We call that just addition in Rn. That's pretty standard. Scalar multiplication in Rn is another very important idea. And that is just taking any scalar, any number, any non-vector quantity. So just think of these as real numbers times that element of Rn. We define that just to be the result of taking that scalar to each component and multiplying it on each component of the vector in Rn. So these are big ideas, addition and scalar multiplication. We are viewing right now, we're really analyzing Rn for various values of n, right? R equals 2, R2, R equals 3, looking at R3, Rn in general we're looking at. But keep in mind that Rn, we are trying to eventually extend these ideas that hold in Rn. We're going to see that these ideas have vector space Rn extend to other types of vector spaces other than Rn. And in all the vector spaces we talk about, no matter how abstract they seem, this idea of defining addition and scalar multiplication on a certain set of elements, these being elements in Rn, this is crucial to our bigger picture kind of understanding of what's going on. So addition and scalar multiplication, be sure we know what those mean. Okay. Now it turns out Rn has a property that we would refer to as being closed under addition and scalar multiplication. Typically when we are writing these vectors, if I'm writing by hand, I will use these little arrows above, these little harpoons. But you'll notice in the book, vectors are often denoted in bold, bold-faced font. Since I can't write in bold very easily, I'll have to use little arrows, these little harpoons, to indicate I'm referring to a vector. Yeah, so let's see what this means. Rn is closed under addition and scalar multiplication. What are we really saying? Let's get at this way. Just 1 second. Sorry about that, a little technical difficulty. We left off just now, we were mentioning that Rn is closed under addition and scalar multiplication. What does that mean? It just means that if I have two elements of Rn and I add them together under this definition of addition, then with this definition of what it means to add our two vectors, the result will also be in Rn, right? If u1 and v1 were real numbers, u1 plus v1 is still a real number. You add two reals, you get a real. Same with the second components all the way up to the nth components of this sum. This is what it means to be closed under addition. When you add two things in the set, you get something back that's still in the set. Two things in Rn add to be something in Rn. A scalar multiplication, being closed under scalar multiplication, means the same thing. Once I multiply by a scalar, a non-vector quantity, so long as I started with something u in Rn, I end up with another resulting vector that's in Rn. In this case, it's got to be true, since if C is real and all these components of U are real, well then C times U1, that's real. C times U2, that's real. C times UN, all those numbers in those components are still real. So this scalar multiple of U is also an element of Rn. That's all it means to be in Rn, is that all your elements, all your components are real numbers. So that's what we mean when we say that Rn is closed under addition and scalar multiplication. Start with two things in these Rn, adding them will result in something in Rn. If you take a scalar multiple of something in Rn, you're still in Rn. And we'll see that that might sound like it would have to be true, but we'll see there are plenty of cases that we'll run into where that's not going to be the case, where we will describe sorts of sets that aren't closed under addition or are not closed under scalar multiplication. We'll see quite a bit about that in the next video. Okay, so Rn equipped with this addition and scalar multiplication that we defined is what we call a vector space, and its elements are called vectors. Now I want to be clear, there are many types of vector spaces. We are looking at a very specific one, Rn, described the way we've described for now. We're going to really develop Rn pretty thoroughly, and we'll see we can extend what we learn about Rn to describe less intuitive vector spaces later. But anyway, if we have a vector space, the elements in there, these vectors in Rn, those are called vectors for whatever vector space we're referring to. In Rn, the vectors are just sets of real numbers, n of them, in a specific order. Okay. Remember, when I say in a specific order, I just mean that if you change the order, you have a different element in that vector space, a different vector in that vector space. So finally, let's start talking more in terms of vectors and stop saying elements of Rn. I can start calling these vectors now. A given vector u equals 3, 4, -5, -6, v equals 1, 2, -1, -2, and w equals 1, 1, 1, 1, 1. Let's compute a few things. Let's compute u plus v, -3v, and w plus u. I'm going to do this off to the side here. Notice I said actually if possible, which might indicate that some of these might not be possible. So let's start with u plus v. It's just as simple as you would think. Take your vector u plus your vector v, and we know by our definition of addition up here, this means we just add component-wise. If you've done this before, this is going to seem extremely boring. You might skip ahead. If you haven't, pick it up quick. So u plus v is just this little vector in R4, 4, 6, -6, and -8. Okay. So -3v, let's see what we get for this. Well, that's a scalar multiple, right? -3v, a scalar multiple of v is just -3 times this 1, 2, -1, -2 vector. And we saw by our definition of scalar multiplication up here that the way to do this is take the scalar to every component on its own. -3 times 1, -3 times 2, -3 times -1, and -3 times -2. Right? So pretty easy to take a scalar multiple. What about this last one, w plus v, w plus u? Maybe pause the video here, take a second with this, see what happens. Hopefully you've had a chance to do that if you'd like to. I'm going to walk through this one. Notice we have a problem right away. W and u, here's my u, here's my w. These have different numbers of elements. U is an element of, that's what this little symbol means. U is an element of R4 because it has 4 real numbers as its components. But W is an element of, again, that symbol there means is an element of R5. We've got 5 ones sitting there. So if we were to try to add these, take W plus U, this wouldn't work. We can't add component-wise, like our definition of addition requires, because we don't have corresponding entries, right? We'll run out of entries to add together. And so, what do we get here? We get nothing. Can't do it. It's impossible. It's ill-defined, but I'll just write impossible. Okay. So be sure when you're trying to add vectors, they have to be part of the same vector space Rn. R4 and R5 are not the same vector space. Rn, when we describe Rn in general, we're always thinking that any of these calculations have to be amongst compatible elements, right? They have to be at the same n. when we talk about Rn. Now let's do something pretty interesting. If you haven't had a lot of experience with vectors, I think this might be pretty important for building intuition about them. So let's graphically interpret a plus b equals vector 1, 3 plus vector 2, 1 comes out to 3, 4. Right, there's nothing magical about this mathematics. A plus b, I'm saying a is 1, 3 and b is 2, 1. When we add them, we get 3, 4. 1 plus 2 is 3, 3 plus 1 is 4. So nothing magical about this statement. I just want to see visually, how are we thinking about what vector addition looks like? And I want to see visually, how are we thinking about what scalar multiplication looks like? 2a equals 2, 6. So let's see this. Let's draw some pictures. I'm going to start with the easy one over here, 2a equals 1, 6. Remember, we're already saying a is the 1, 3 vector, which makes sense with this statement, right? That agrees with it. If we multiply 1, 3 by the scalar 2, we'll get 2, 6. So I want to draw a little picture here. If I was to draw vector A, that would go 1 unit in the x direction, 3 in the vertical, right? This is our standard way of thinking about graphically what these elements 1, 3 of R2 would really represent. You can think of it as representing a point, but I want to think of it as representing a position vector. That was a terrible vector. Let me draw this easier. Give myself some space here. Okay. 1, 1, 2, 3. There it is. There's my vector, right? It goes to the point 1, 3 from the origin. So that is our vector. And we're asking to now draw what is represented visually when we say that 2a equals 2, 6. But we know this is our vector, A. If we now plot what 2, 6 looks like, well, we go 2 units here and 6 here. If we did this perfectly correct, it should look like the same direction as the previous vector. We even get a different color here, just twice as long. Right? And it looks pretty good. This is our 2a vector. So this is fairly important, when we multiply a vector by a number, I'll just make a note of this. When we multiply a vector a by a number, take a scalar multiple of it, this multiplies length of a by the absolute value of c and reverses the direction if c is negative. So for example, if I was to sketch negative 2a, that would go down in this opposite direction. It would still have the same length as 2a. It would just go about like that. Something like that. It's not exact, but it looks pretty good. Okay. So visually, that's what we think of when we talk about a scalar multiple. We think that the scalar scales the length of the vector, right? If I multiply a vector by 2, I scale the length up by a factor of 2. If I multiply by a half, I scale it down by a factor of a half. If I multiply by a negative, I do that same scaling on the length, but I also reverse the direction. It makes pretty good sense for vector addition to reverse the direction when we do that. Let's look at the other part. Interpret what a plus b equals 1, 3 plus 2, 1 equals 3, 4. Interpret what that means, and again, with a picture. I am going to erase this picture, so maybe pause really quick. I'm going to erase all this. Maybe pause really quick if you want to take notes about that before I move on. But now let's do the other part. A plus b equals 1, 3 plus 2, 1. So I'm going to start just by sketching these two, the vectors I'm starting out with. And I don't care if my pictures are perfect, but I'm going to try to get the qualitative idea across. If I sketch A, that again is 1 here, 3 here. So it stretches from the origin out to that point. Now, if I sketch B, that vector goes, in fact, let me clear out my labels for now. There we go. Okay, maybe I'll zoom in to make it easier to see. There we go. 1, 1, 2, 3. So that is our vector A. Now, if we sketch the vector B, that's the vector 2, 1. So we go 2 in this direction and 1 upward. And we get this vector. Okay. Now, what does it mean that we're saying, back over here, that the sum of these two, A plus B, is the vector 3, 4? Well, let's plot what 3, 4 looks like. 3 out in this direction, 4 in this direction. I did this right. It should look like it's about here. Let me sketch that. What we want to notice is that this sum of the two is exactly what you would get if you took your vector A first, right? This was our vector A over here. But the sum is exactly what you get if you started by thinking of A as being an amount of displacement from the origin and follow that displacement as indicated by A. But then think of this other vector B, this guy down here, as being an additional displacement that you also want to apply, right? Adding these two displacements, these two vectors, you can think of it as meaning apply one displacement after another. So wherever I ended up with after displacing by A, now I want to displace by the vector described here with arrow B. So kind of follow a parallel direction to B and the same distance. You should get to that same point that your sum vector ends up at. You might notice we're actually forming a little parallelogram here with A and B. Here's something like A, here's something like B. If you form a parallelogram with your two vectors, then the sum of those is just the long diagonal all the way across from their common tail to the opposite side of the their common initial point. A and B is a common initial point, the opposite side of the parallelogram. That is the sum. Sometimes that's called a parallelogram rule for addition. Another way to think about this addition is that you have your first vector, A, and then you follow that by vector B. And the vector from your original initial point to your final terminal point is the sum. And if you draw both of these pictures, the parallelogram rule or this, the triangle rule, if you do it very accurately either way, this sum vector in both cases will look like it has the exact same length and they'll both look parallel to each other. They have the same direction, which means they're really the same vector. Okay, so that's how we interpret this addition of two vectors. It's like applying one displacement, vector A in blue here, followed by, so it's followed up directly after that by another displacement described by your second vector. The overall displacement from where you started to where you ended, that's your sum of the two vectors. You can think of this as with a rule for addition or a parallelogram rule for addition or a triangle rule. Okay, well, let's move on a little bit more and talk about some special vectors in Rn. So there are a couple of these, two big ones, the zero vector, On. That is just a vector full of n zeros. So it's in Rn, there's n of the entries here. Kind of written it lightly, I'll darken this up. There it is, where there are n zeros listed in this vector. right? That's the zero vector. It's important for lots of vector spaces. The zero vector, it turns out, is required to be in anything we call a vector space. So for Rn, the vector space Rn, the zero vector is just the list of n zeros, right? It's the origin if you think about it that way. A negative of a vector, we want to define what that is. Well, the negative of a vector, we're just going to say that's the vector multiplied by the scalar -1. It's the -1 scalar multiple of the vector. And when we write this, -1 times a vector u, we're just going to write it as -u. So just like we have negative numbers, this is what we'll think of negative vectors as being. Yeah, and we really just think of -u as being the exact same length as u, just in the exact opposite direction, 180 degrees opposite. Right, in the plane, we already described this a little bit above. This is u, -u is just about like that. And in three-dimensional space, same idea. They're just opposite direction, same length. And this is actually nice because it gives us a way, now that we have a negative idea, it gives us a way to define vector subtraction. It's just addition of a negative. We're going to say u minus v is just u plus the negative of v, right? -1 times v. And so if you go through that scalar multiplication, -1 times your vector b, and the addition, the way we've defined it on Rn, this ends up just being the component-wise subtraction of your two vectors, u1 minus v1, u2 minus v2, and so on. Again, pretty easy. If you haven't done it before, probably catch on to that real quick. And now we define all other operations on Rn in terms of addition and scalar multiplication. This is an important idea. It's really with an addition and scalar multiplication that we define Rn to be a vector space. A vector space comes along with a specific definition of addition and scalar multiplication. So Rn, equipped with our definitions, is a vector space. And some properties that hold for elements in this vector space, vectors in this vector space Rn. Given scalars c and d and vectors u, v, and w in Rn, if we want to add two vectors, u plus v, doesn't matter which order we add in. u plus v is the same as v plus u. Also, we have associativity of addition. If I had u plus v plus w, I could add the last two first and then add on the first one. Or I could add the first two first and then add on the last one. Doesn't matter. We can group these additions in any order we please. Property 3 describes the zero vector, right? The zero addition property. Maybe I should call this the additive identity property. A vector u plus the zero vector in Rn is the same as adding 0 to u. So again, we have that associativity, that's commutativity of addition by the zero vector. But all of those, no matter which side of u we add 0 to, we still get the u vector back. Addition by 0 doesn't do anything, as you would expect. 4 here says that u plus its negative is 0. Now we're just saying that does hold in this vector space Rn, just like you'd expect to hold with numbers. Property 5 says we can distribute a scalar across a sum of vectors. Property 6 says we can distribute a vector across a sum of scalars. So this is very nice. Both ways we can distribute. Property 7 says if I have two scalars multiplied on a vector, really you can apply those scalars to the vector in any order you please. You could apply d first, or you can multiply the two scalars together, then apply to u. You have freedom with that scalar multiplication. Finally, and very uninteresting, the multiplicative scalar multiplication identity. 1 scalar 1 times a vector doesn't change the vector. A lot of these are probably pretty intuitive, but it's important to know that in this vector space Rn, all these kind of intuitive properties still do hold. Okay, let's get into some important stuff here, linear combinations. We'll see this idea of linear combination is crucial for talking about vector spaces in general, as well as for talking about a specific vector space Rn. So notice that these rules up here let us actually write an addition of scalar multiples of vectors unambiguously. If we write AU plus BV plus CW, We don't have to add any parentheses there to indicate what operations need to occur first, or to indicate what order this addition has to be carried out in, right? We could mix this up in very strange ways. When we write AU plus BV plus CW, there's really only one meaning you can derive from that based on these properties up here. Well, when we write something like that, this would be called a linear combination of vectors U, V, and W. A linear combination we think of as just being some parts U plus some parts V plus some parts W, where the amount of each, parts you have of each, are indicated by these scalars A, B, and C. So a linear combination is a sum of scalar multiples of vectors. Here's a scalar multiple of U plus a scalar multiple of V plus a scalar multiple of W. That is called a linear combination of those three vectors. We're going to talk about linear combinations of many numbers of vectors. Linear combination of 2 vectors, or 3, 4, 5. Here, just to get us started, that's what a linear combination of 3 vectors looks like. Now, given vectors v1 through vn in Rn, in vector space Rn, we say that a vector v in Rn, remember this little symbol just means v is an element of Rn. But given this set of vectors v1 through vn, we say a vector v in Rn is called a linear combination of those n v vectors, v1 through vn, if there are scalars c1, c2 through cn. Oops, sorry. I'm saying I have m of these given v vectors. Let me fix this real quick. M of them, right? You don't have to have the same number of v vectors here as your dimension in space, sorry. So let's reset here. Given vectors v1 through vm in Rn, so each of these is in Rn, we say a vector v in Rn is a linear combination of those m vectors if there are scalars c1, c2 through cm. So a scalar for each one of those v1 through vm, so that your v is c1 times v1 plus c2 times v2 plus all the way out through cm times vm. If we can write v as a linear combination of these vectors, it means that we can find scalars to put in here to make this equation true. That would mean v is expressible as a linear combination of v1 through vm. Let's see this as an example here. Is the vector 6, 13, 9 a linear combination of the vectors 1, 1, 2, 1, 2, 1, and 2, 3, 4? Let's see how to work this out. I mean, we don't have to know anything more than we've already seen. All we're going to say is, if so, we can find scalars C1, C2, C3, right? That's like these scalars up here. You have as many scalars as you have vectors that you're trying to express a linear combination of. In this case, 3 of them. I have 3 scalars. But if so, if this 6, 13, 9 is a linear combination of those given vectors, then we can find scalars C1, C2, and C3 so that the vector we start with equals C1 times the first given vector plus C2 times the next vector plus C3 times the last vector. And so really, we just look at this and we try to solve this system of equations. You might say, well, this doesn't look like a system of equations, but I claim it is. I claim it's just kind of packed up in a strange way, but this really is a system of equations. If we take the right-hand side and put this sum of scalar multiples all together, well, what do we have? In the first vector, we can take this C1 and multiply it through the vector. Do the same for the next vector. And the same for the next one. And now we can add these vectors. We know how to add vectors in R3. We just add component-wise. The first component, just adding components, adding this guy, and this guy, first components of the three vectors, we get C1 plus C2 plus 2C3. Next, we get C1 in the second components, we get C1 plus 2C2 plus 3C3. Finally, in the last components, we get 2C1 plus C2 plus 4C3. But remember, we're saying on the other side, this still equals 6, 13, 9. And now we take a look. Well, what would it mean for two elements of Rn to be equal? 6, 13, 9 equals this vector over here, the one whose first component is C1 plus C2 plus 2C3, second component C1 plus 2C2 plus 3C3, and so on. What does it mean for those to be equal? It means that each component is equal on both sides. The corresponding components are equal. So let's write down a system of equations that this gives us. Equating first components on the right side with the first component on the left side, we get an equation involving C1, C2, and C3. Now for the next one, C1 plus 2C2 plus 3C3 equals 13. And the last component on the right side is 2C1 plus C2 plus 4C3 equals 9. There we have it. So this is pretty common. When we're trying to express a given vector as a linear combination of other given vectors, it amounts to solving a system of equation for those scalars needed in the linear combination. That's a common theme here. And let's go ahead and solve this. This will be a good opportunity to actually introduce how to use a little bit of MATLAB or Octave, whatever you prefer to use. Let's write this over here. But let's write the augmented matrix for this. Right, remember, if we want to solve a system like this, typically we pack it up into an augmented matrix. 1, 1, 2, 6, 1, 2, 3, 13, 2, 1, 4, 9. And the idea is we take this and we solve it. Remember, to solve for us means we're hoping there's a unique solution, but even if there's not, to solve meant that we wanted to reduce this down as far as we need to in order to unpack it and solve it. I'm going to take it all the way in the matrix to reduced row echelon form. I'm just going to say reduced echelon form. And I'm going to do this using Octave. So Octave is an online version of, an online free version of MATLAB that will work perfectly well for our purposes. There are differences certainly between MATLAB and Octave. But since we're doing this virtually, I think Octave will be a good choice. Let me share my screen. Here we go. So you'll go to octave-online.net. That will take you here. And the way you operate with this is, at least for our purposes, we're going to use it mostly just like a big calculator to do complicated calculations on matrices. That's our big goal with this. And so a couple things we can do, if we want to do something to a matrix here, the basic startup would be to enter that matrix into this big calculator, Octave. So for example, if I wanted to do some sort of operations on this matrix, I need to enter it into Octave. And to do that, I should give it a name. I'm going to say A equals, right? We usually use a capital letter for these, for matrix. And to enter your matrix, you want to use square brackets to open the matrix and order and list in order your first row. You can separate the numbers in that row with a comma or just a space. Space is pretty typical. So in this case, let's see if I can do it simultaneously here. I'll have 1 space, 2 space, 6. That filled up my first row. Now to get to the next row, I use a semicolon. And we start listing the next row, separated with spaces. 1 space, 2 space, 3 space, 13. Semicolon to end the row, jump to the next one, 2 space, 1 space, 4 space, 9. And that's the end, so we are going to close those square brackets. Now, if I just press enter, it's going to show me the matrix that it reads, right? And this is nice to do, especially when you're just doing quick calculations, to make sure you entered what you intended to enter. It's easy to make little mistakes. It's nice to see that rectangular array like this. If you don't want that, if you just want to suppress the output, not see this listed out this way, you just want to store the matrix in here, not see it spit back out. Enter A like we did before. I popped up my previous entry, by the way, just by pressing the up arrow on the keypad. Get that matrix entered this way, and to suppress the output, you can press semicolon at the end. And then if I press enter, it'll say that it's accepted this, but it's not going to spit out that rectangular array and show it to you. It's good to check that, though. I kind of like to leave that unsuppressed without a semicolon. Now, how are we actually going to do this to get the reduced row echelon form? Well, it turns out we have an operation for that built into MATLAB and Octave. It is just, remember I mentioned most books call reduced row echelon form RREF form. It turns out that's a command built into these programs. I can just write RREF of A. RREF, open parentheses, A, close parentheses. And when I press enter, this is going to do the row reduction for me. Now, it is crucially important that you can do these row reductions on your own by hand. Maybe this will be a good way to check your work using Octave or MATLAB. Or maybe when the row reduction has been something we've done over and over, and you've moved on to just using it to confirm other things later, where row reduction is really not the focus, maybe this is a good tool to use in those cases. But be sure you're not using this as a crutch. You want to be able to definitely do this on your own. But what do I get? When I run this, I get the identity matrix in the left square. Right? We said that's good news. That means there's a unique solution. We get the identity matrix in the left square. And the right-hand column became, it looks like, -534. Oops. -534. And so now if we unpack this, all it's telling us is that 1 times C1 plus 0 times C2 plus 0 times C3, I won't even write those, equals -5. The next row would tell us, if we unpacked it back to equations, it would tell us 0 times C1, not even going to write that, plus 1 times C2 plus 0 times C3 equals 3. And likewise, the last one would give you C3 equals 4. You have those coefficients needed in your linear combination now. So when we ask, is 6, 13, 9 a linear combination of these 3 vectors? Well, the answer is yes, right? If we take -5 for C1 here, 3 for C2, and 4 for C3, then this equation would be true. And you can check that. I'll even write this down here. I'm going to write answer, yes. 6, 13, 9 equals -5 times the first given vector plus 3 times the next vector plus 4 times the last vector. That was our C3 value. Okay, so I would say, yes, we certainly showed 6, 13, 9 is a linear combination of those given vectors. Here, I would describe this as 6, 13, 9 described as or expressed as a linear combination of the given vectors. So I'm going to often kind of describe how we would talk about the things we're doing. If I was saying, express a given vector as a linear combination of some other vectors, this is the sort of answer I would look for. If I just said, is this a linear combination of these guys? You do all the work and see if you can find your C values. And in this case, you'd answer, yes, it is a linear combination. This is how we would talk about this. This is 613.9 expressed as a linear combination of those given vectors. Okay. We've seen a little bit of Octave. Same commands will work in MATLAB. Be sure that you try those out. Make sure you have those as resources. It's important to note here, we wrote everything as row vectors in Rn, right? We wrote them horizontally. Sometimes we represent elements of Rn using column vectors. And in fact, it's very useful in many cases, especially when dealing with systems of equations. And often when we want to do that, these column vectors, we'll express them just by column matrices. So square brackets with columns and numbers in them. Column vector is just a column matrix. If we wanted to add to, we might write something like this, U1 down to UN plus V1 down to Vn equals something like this result over here. So same rules of addition and scalar multiplication when we write them with columns. We're simply using columns instead of rows. No big deal. And so to end this video, I do want to briefly go over a review of complex numbers. It turns out a lot of this stuff that applies in Rn applies in Cn, the space of n-ordered complex numbers instead of n-ordered real numbers. So let's review some complex numbers so we remember that we can do a lot of the same arithmetic, row operations, things like that, on matrices with complex entries. We won't do a ton with complex here, but I think it's worth it to review this in case you practice problems or see problems on a quiz that have some complex values here and there. So a brief recap of complex for you. Basic definition, a complex number z is usually what we use, has the form z equals a plus bi, where a and b themselves are real numbers and I is the square root of -1, the imaginary unit I. I squared is -1. I itself is the principal square root of -1. If we want to express these complex numbers graphically, we think of graphing them as points in the complex plane. The complex plane just being a real axis and an imaginary axis. Whatever this A value is, we plot that in the real direction, the horizontal, and B we plot along the vertical. We call that the imaginary direction. And so it's useful to describe the different parts of these complex numbers. The real and imaginary parts are defined as follows here. Given a complex number z equals a plus bi, that number a is the real part of z, denoted re of z equals a. And that number b, not b times I, but b itself is the imaginary part of z, denoted im of z equals b. So for example, if I wrote down, I don't know, z equals 2 plus I, then in that case, the real part of z is 2, and the imaginary part of z is 1. It's not 1 times I, it's just the coefficient on I here, which is implied to be 1. That's pretty important. So it shows us that when we're graphing, we're really graphing the real part on the horizontal against the imaginary part on the vertical. Now, we don't care so much about visualizing complex numbers in this class. What we do care about more is just being able to do the basic operations that we do with real numbers, only with complex numbers, which you can also do in Octave and MATLAB, right? You can enter matrices with complex values. It can handle those. Well, let's remind ourselves about how operations on complex numbers work. Given complex numbers z1 equals a1 plus b1i, and z2 equals a2 plus b2i, to add z1 and z2, you just add real parts, a1 plus a2, and imaginary parts, b1 plus b2 times I. Another way of stating this rule for addition is that the real part of the sum is the sum of the real parts, right? The real part of z1 was this a1, the real part of z2 was this a2. When we added those, we got the real part of z1 plus z2. Similar for the imaginary parts. The imaginary part of the sum is the sum of the imaginary parts. And I should have put a z2. just then. Okay, so addition is really just very simple. You're just adding compatible parts. The stuff that has an I gets added, the stuff that doesn't have an I gets added. To multiply to, you still just follow basic rules of multiplication on real numbers. You write Z1 and Z2 out in their form like this, and you FOIL this. A1A2 plus A1B2I plus A2B1I plus B1, B2, I times I. So I'll write I squared. But just remembering that I equals the square root of -1, right? If I equals the square root of -1, then I squared must equal -1. So this guy just flips everything negative. So let me write it here. The sum of these two, actually I'm gonna, already. Since this I squared is gonna turn into a -1, then that will leave this as just a real quantity. I'll put it with the other real quantity. Minus because of this -1. So that's all the real stuff we have. Everything else is attached to an I value. I can factor the I out to the back of the rest of that stuff, and this is what I get. So here we can say the real part of Z1 times Z2 is all this stuff, bit of a weird quantity. And the imaginary part of that product is all this stuff. Not times I, the imaginary part itself is just that real number, A1B2 plus A2B1. Now, I don't suggest that you try to memorize these formulas for how this multiplication comes out, what the real stuff and imaginary stuff splits up into. I expect you would just multiply these two numbers, right? For example, if I had, I don't know, Z1 equals 1 plus I, Z2 equals 2 minus 3I, these are easy to multiply. You just use your standard FOIL method. So like we get 2 minus 3I plus 2I minus 3I squared. But then we remember I squared is a -1. So we get 2 plus 3. The -3I plus 2I is -1 copy of I. This is how you would actually do the multiplication, to be clear. You probably don't need to memorize this formula. Just remember that I squared equals -1 and FOIL it out as usual. Now, to divide two complex numbers is a little complicated. So let's see how to do it in general over here. And then we will go through an example. For this one, the key here, you might remember this, is we have a complex number in top and bottom, and that tells us we really can't easily separate or parse out what the real stuff is and what the imaginary stuff is. So if I wanted to plot this quotient, Z1 divided by Z2, it would be very difficult. I have no idea what my real and imaginary parts are, how far to go in the horizontal and vertical. So to isolate the real part and the imaginary part, the standard way to do this is to take your complex number divided by another complex number and multiply by something called the complex conjugate in top and bottom. So we need to define this. The complex conjugate of a complex number like Z1 up here is just the exact same number, except you reverse the sign on the imaginary part. So if you started out with a plus B1I, the complex conjugate has a minus B1I. This is the complex conjugate of Z1. And we denote it with this little bar. You might hear this even just referred to as Z1 bar. Now, one nice property of complex conjugates is that when you multiply two of them, Z1 times its own conjugate, let's see what happens. That's Z1. Here's Z1 conjugate. What happens when we multiply this? you might see this is a difference of squares. So we know how it comes out when we multiply. And we know the I squared is -1. So it flips that negative to a positive. This is very nice. When we multiply a complex number times its conjugate, we are guaranteed to get a purely real number. Right? So let's note this right away. The imaginary part of a complex number times its conjugate is 0. Doesn't exist, goes away. And this shows us a very nice, easy formula for computing a product of a complex number times its conjugate. It comes out just to be the sum of the squares of the real and imaginary parts. So this is very valuable up here. What we're going to do here is we are going to take top and bottom and multiply by the complex conjugate of the bottom. We're doing it to top and bottom because we're trying to balance this fraction. This is what we get. And let's see what happens here. Multiplying the bottom together is easy. It's going to be the square, the sum of the squares of the real and imaginary parts. Right? That's what we saw down here. Just happens to be we're using Z2 instead of Z1. But the top we just FOIL out. Let's see what the top gives us. A1, A2. The other real stuff that's going to come out of that will be positive B1, B2. Plus, looks like all the imaginary stuff that comes out of that is going to be A1 times negative B2. In fact, I'll put that at the back since it's negative. And B1 times A2. All that's going to have an I attached. And this is useful to us because we have a real number down here. We can split this up now. This is A1, A2 plus B1, B2 all over the sum of these squares. And notice all of this is a real number. That's just a real number. There's no i's in there. Plus, we split up the other part. And so in this way, multiplying top and bottom by the complex conjugate of the denominator shows us a way to really split this up into the real part and imaginary part. So let's do a quick example of this. If I said, even with these same Z1 and Z2, let me divide these now. What do we get when we divide these? Well, we're dividing 1 plus I divided by 2 minus 3I. And keep in mind, you might have to do this sort of thing if you were doing row reductions on a complex matrix, because you might have to scale a row. And if all of the entries are complex numbers, scaling might involve dividing by another complex number. Right? If I had, I don't know, a 2 plus I in this row and a 1 in this row, and I wanted to use this guy to get rid of this guy, I would need to multiply this guy by something like 1 over, I'd need to do something like 1 over 2 plus I times this row, subtracted from the bottom row. Right? So you might have to do some division of complex numbers with complex numbers. But let's see how it works here. Multiply top and bottom by the conjugate of the denominator. 2 plus 3i. The denominator should be simple. It's just going to be the sum of the squares of the real and imaginary parts of the denominator. So 2 squared plus 3 squared. Easy. And the top we just multiply out. FOIL this guy, 1 plus I, with 2 plus 3i. So we have 2 plus 3i plus 2i plus 3i squared, which equals, remember 3i squared, that's really just -3. -3 plus 2 is -1, plus 5 copies of I total, 3 of them plus 2 of them. And in the denominator, it looks like we have 13. So this is -1/13 plus 5/13 I. Right? So this is what we're really describing. If I'm dividing complex numbers, it's not division as we typically think of it. The only point in actually doing anything to an expression like this, 1 plus I over 2 minus 3i, is to parse out what the real and imaginary stuff is there. And we do it this way, multiplying top and bottom by the complex conjugate of the denominator. So I do just want to finish off by mentioning that the complex vector space Cn, this just denotes complex vector space. So it really is going to operate pretty much for our purposes the same as Rn. Here we're just going to say the set of all U1, U2, all the way out through UN, such that U1, U2, UN are each complex. The set of all of these things, I should say the set of all vectors of that form is a vector space, just like Rn is a vector space. If you take two objects of that form, complex numbers, n of them all ordered, add two things of that form, you will still have something of that form. So this complex vector space is also a vector space, and it turns out Rn is contained inside of that. You might see that these double strikes or not. But this is a big idea here that just like we can work on Rn the way we have, we can also work on Cn. It is harder to visualize since, remember, each of these numbers has kind of two parts to it on its own, a real and imaginary part. So it gets a little more complicated, but formally the mathematics works out the same way for virtually everything we do in this class. Okay, so that is it for this section. I think that's plenty. You might run into working with some complex values in practice problems or in the quiz. Be sure to practice with those. Other than that, let's save the rest for 1.4, where we are going to talk about subspaces of vector spaces. Okay, that's it for this video. Thank you for your attention.